All right. So we're going through everything we did. This isn't too loud. This is good. Okay. Okay. All right. We're going through basically everything we did today in really light speed. The goal isn't to give you like perfect understanding of how to do every function, but really a sense of where to start, how to at least implement it with a simple data set. And let's see. So yeah, and the main purpose of these techniques, again, kind of is to evaluate network features with some sort of significance test. How do you know how homophilous your network is? Is it more homophilous than you expect by chance? What sort of factors influence people becoming friends with each other? So I hope you've all gone to Dropbox and were able to download the files. Okay. All right. So we're going to jump in. We're going to be using this this file called master code start here. And I want to just thank, I created this lab, but I borrowed tons of pieces from tons of people. Let's see. Great. So the first thing you have to do before anything is set your work directory. I assume you all are comfortable doing that. Basically, you just let your computer know this is where all my files are. You want to set your work directory to where all the lab files are. So that includes all the R scripts and the data. If you're having trouble figuring out how to set your work directory, again, we got people back there. So we set our work directory. All right, so this is a slightly strange script I did. What I try to do is break it up into pieces. So we have all these things that are file edit. It's basically just opening the R script that we have. You can break R scripts up like this, and it can make life, it can make your code a little bit more easy to read through, but you can also do it in a way that will make everybody hate you. So be very careful if you do it, because I'm not sure I consider it good practice. On the other hand, if you are forced to publish your R code and you really don't want people to use it, use lots of source, and it'll help you out. All right, so just some preparatory stuff. We're going to be deleting everything in our workspace. I recommend actually closing your R studio and reopening it if you haven't, but otherwise we're just going to delete all the objects. And then we're going to do this little garbage cleaning function. It just gets rid of things in your RAM. R is a little memory intensive at times, and so it's not good at getting rid of things that you've already deleted. So we're going to install a bunch of packages. This is a function that, these are the packages that we're going to be using. You got tidyverse, statnet, ERGM, ggplot. Most of these you should already have. And if we just run that, even if we've already installed them, we have this nice function here that will only try to install them if it sees that you haven't had them installed. For me, I had them all installed, so nothing bad happened. But you want to run that because we're going to need these packages to do basically everything we're doing today. So then we're going to load these libraries up. This is what you have to do basically every time you start working with R. You're loading your library. You're setting your directories. This is every time you use R. This is what you want to do. So we're loading our tidyverse, statnet, ggplot, SNA, epimodel, and netdiffuser. We sent an email, I think. So statnet, you might get a indication in your console that says something like, your statnet's out of date. Ignore it. It seems to be a bug. It went away for some reason for me, but it might be there for you. If you try updating it, it'll just give you the same version of statnet you already have, unless yours is really old, in which case, please update. So now we're going to load our data. We're going to be working with this this data set that I think we've worked on multiple times in our labs. It's a version of AddHealth. Well, it's meant to look like AddHealth. It's not really AddHealth data. If we want to look at the data itself, we could use a view function, and this gives us like an Excel-like table, which has all the rows and columns. We have these different variable names. This is considered an adjacency list. The idea is individuals are allowed to nominate a certain number of friends, and the friend identifier will be a number, which is an ID of the other friend that they're nominating. And they can nominate up to 10 friends. Most people don't. And so just is really good to always have a good sense of what your data looks like. So we're going to be using that data. And let's see, yeah, I have a, let's see. All right. So we're going to want to convert our data into a smaller adjacency list. We want to get rid of all the things we don't care about. So we're using dplyr select function. Just to give you a sense of, this is a pipe. If you guys aren't familiar with pipes, basically the pipe is just saying we're using this data set's HS base, and we're going to, with that data set, we're going to do these other things. It's functionally equivalent to if we just delete that and we put it right here, it'll do the same exact thing. It's just a neater way to sort our data. Usually you string pipes a lot together, but that can be really complicated and confusing. We're not going to do that. So all we're doing here is we're making a new data set, and it's just including variables that we care about for this lab. So we're selecting a bunch of these different variables, and we can look at this data set. And let's see, so you view this data set, and it's the same data set, just the variables that we have. All right, so we're also going to, so this data set has tons of different simulated schools, and we're going to just focus on the first one. And the reason why is because a lot of the functions that we learned earlier today get really complicated when you have multiple different networks. So we're just focusing on one network. And that's what this is doing. This is saying just keep AHS adjacency list if it's if this value count equals 1. So if we now look at the data set again, it's the same thing, but now we only got 71 rows, and everybody's got count equals 1. So we're just getting rid of some data that we don't care about. All with me? Awesome. All right. So we want to now convert our adjacency list to an edge list. We've learned about these different data types before, these formats for data. So right now, again, we have different columns representing each friend nomination we have. What we instead want to do is just have it so that there's one column that represents who you nominated, and then lots of rows for all the different nominations you sent. It's really useful for when we convert things to matrices. So this gather function, it's a little complicated. It's, again, based on a dplyr language. But the idea here is that we're collapsing these 10 different columns that have the people that we're nominating as friends into a single, into 2 columns, basically. One that's the identifier of what the column is. The other that's an identifier of the value. So again, we could look at this edge list that we just created. It's not really an edge list quite yet because we have all this other stuff, but it's mostly an edge list. So you see we have like this new column alter label, which is the variable name that we had, and we have the target. And that's the people are nominating. And you see a lot of these 999s. Any idea what those are? Yeah, they're missing data, right? They're people that were nominated who aren't actually in the survey, and we don't know what to do with them. So for now, we're going to get rid of them. We're also going to, just for the sake of preference, I guess, we're going to rename the ID variable to just ID before it's ego and ID. And so we're getting rid of the target people. So we're saying if it's 999, just pretend it's not there at all, delete it. And now we're going to get rid of all the other information in this edge list by just, here we're saying just keep ID and target. So if we look at this new data set, we finally have an edge list of everybody in our school. So ID is the people who are sending the nominations, and target is the receiver of the nominations, right? So ID 1 nominated person 52. We scroll down, person 52 seemed to only have nominated 1. He reciprocated the tie. So we have this edge list, and right, just double check I didn't skip anything. Okay. All right, so we got this edge list, right? And now we're going to start using functions from the SNA package. So there are 2 really common packages that people use when they're doing networks with R. There's iGraph and there's SNA. They have a lot of overlap in their functions, you'll find, but SNA does more of the things that we need for today. So we're going to convert our edge list to a graph object called G. Now, if you look in your environment, you'll notice you have this thing G, and it says it's a list of 5, and it has nothing remotely intelligible in here. Welcome to R. This is a lot of objects are going to be that way, but so right now we don't have a great sense of what this object looks like. But if we print G in our console, if we just say G and we print it, we can get this whole list of information about this network that we just put in there. So we have 71 vertices, meaning we have 71 different people in our network. This is a directed network, meaning that people can both send and receive ties and not necessarily have them reciprocated. And it counts the number of edges, so there's 305 ties in total in this network. All right, so SNA uses kind of a weird syntax for assigning node attributes. So we might want to know, right now we just have edges and we just have names, but we want to bring back information like what gender they are or what grade they're in, because that's going to be useful for when we study how's a network forming, knowing these sort of things. These things often determine who you become friends with. When I was in 7th grade, I didn't have any 10th grade friends. I don't think that's super common. So this is a way of telling the G object to assign this variable grade to our variable grade from our adjacency list. And like if we now highlight GV grade, we'll see these are all the values of the grade. So first person's in 12th grade, second person's in 7th grade. This seems like pretty unrealistic data unless this is the tiniest school ever, but that's okay. So now we're going to assign also whether the gender people are to a different variable in this graph object and whether or not they smoke to this graph object. So then there's a few things we might want to look at. We might want to get degree scores of the network. So we might want to see how many out degree does each person have in our network. So here we see the first person nominated only 1 person, second person nominated 9 people, and so on. So the second person is very outgoing. He thinks everybody's his friend, whereas the first person is not nominating a lot. But then if we look at the in degrees, we might get something different. So like the first person didn't nominate a lot, but some people nominated him. So I guess he's kind of like too cool to nominate friends, but has some friends. Number 2 is the other way around. He nominated lots of people, but not many people nominating him, and so forth. Right. So we can assign these variables now. We have these variables in degree and out degree. We could assign these as node level attributes too. So here we're just saying, okay, we're going to create a variable called in degree. That's another attribute of the people we have here, and out degree. And now we can plot our network with some very simple, not the best plotting algorithms. Functions in R, but we could plot our network. And if you get a function like an error like this, means there's not enough space to show your graph. So I'm going to just expand this, and we're going to try again. And so we got this little teensy network. Really hard to see anything, but this is colored by what is it, grade? And so you have. It looks like you see a lot of the sortivity, right? You see yellow. They all have the same. They're all in the same grade. People are really friends with just other people in the same grade as them. You see the same thing with green and red, a lot of clustering by grade. Let's close this. And you could do the same sort of thing. You could, you could do this by sex, and maybe because the nodes were really tiny, you could increase the node size. So here is friendship by gender. And again, you see a lot of the sortivity. These are things I assume is all review. This is mostly basic sort of stuff. So we've prepped our network data. So we're going to now close this file, and we're going to go back to our master code, and we're going to go to the next step. The next step, we're going to start getting some basic descriptive stats about our network. So for example, you might wonder, say you have a network, and you're interested in is the norm of transitivity really high? Are people often nominating friends of friends? Or are people are they like chimps? They don't care who their friends are, they're not going to become friends with them. You might be interested in this, right? It's a classic sort of sociological question, and so you might get this stat that's indicating how often people are having transitive ties in their network, given how many transitive ties are possible in the network. So you get this number, and it's 0.375. And a big question might be, like, is this a big number? Is it a small number? Anybody have any idea? Yeah, there's no way. you need some sort of comparison group, right? This is just a statistic right now that seems like nothing. So we're going to figure out, does this network have a high level of transitivity or a low level of transitivity? We could do the same thing for getting other network attributes. But so what we're going to first do is we're going to look at the distribution of ties in this network. And we use the dyad census function. This gives us this, this variable that's dyads. And it's counting the number of mutual ties in our network or reciprocal ties. My friend nominated me. I nominated my friend. Asymmetric ties, that's when I'm nominating someone and it's unrequited love. They're not nominating me back. And then null ties, meaning possible ties that were never made. And so we have this dyad information. We know the distribution of friendship ties in our network. And we're going to just assign these two variables. And so we have now our own little rmut is just our own little variable that says 85. It's how many mutualistic ties in here. So what we want to do is we want to figure out, is transitivity high in this network or is transitivity low in this network? And the way you do it is you compare it to random graphs, right? You generate a random graph with a similar structure as the network you have and see, is transitivity higher in this graph than we would in our own graph than we'd expect by chance based on simulating random graphs. So we could do this manually first. I'll just walk you through one example. So we have here, we're just assigning how many simulations are we going to do. We're going to generate a lot of random graphs and look at transitivity in all these different random networks. We're going to prep a little variable that's, we're calling it simchan. It's the number of transitive ties in our simulation. And it's just an empty vector. We're just prepping this variable. It has no information in it right now. But we're going to fill the vector with this loop. So we have this loop that says, for every time 1 to 500, we're going to simulate a random network based on the distribution of ties in our network. So we have this, this function called argument. I'm not sure that's how you normally pronounce it, but basically it's a way of creating a uniform random graph based on a distribution of data. So we can tell them there are 71 nodes in this network we want to create, this random network we want to create from scratch. We want to have 85 mutualistic ties in this random network that we're creating. We want to have 135 asymmetric ties, and the rest we want null ties. And we're going to, so we're going to do it just one time just to get a sense of it. So we're going to set I to 1. This is a good way if you're doing a loop and you want to get a sense of how's this loop working, what's it doing. A really easy way is you first just assign the whatever the variable that's looping that's changing over time to a number like 1. So we're going to the first instance in our loop, and we're going to simulate this network. So now we have this new network that it's like a matrix. So if we did sim g, we're not going to view the whole thing because it's hard. But we could look at the first, I guess that's not how this one's formatted. But basically, it's a network of ties. You can see here, you got all these, is a big matrix filled with ones and zeros that are randomly distributed based on our preconditions that there has to be a certain number of reciprocal ties, a certain number of outgoing ties, etc. And so then we have this network, and then we're going to tell, okay, estimate how many transitive ties, what's the degree of transitivity in this network? And we get this number like 0.05. And so we're going to assign that variable to this, this vector that we created, this blank vector. We're just saying, okay, so the first value of this is now going to be 0.05, and we're going to run the loop. So we run the loop, and now we have tons of different transitivities that we estimate based on all these random graphs based on the distribution of ties in our network. And so we might wonder, okay, do these graphs look like the graph we have? Is transitivity higher in our graph than they were in these random simulated graphs that we created based on a distribution of ties? And this is how we're going to get a sense of whether transitivity is high in our network or low in our network. So here we're going to just convert this vector that we have on the right-hand side of our data set to a different type of object called a tibble. It's just a data frame, basically, with one column. And we're going to use ggplot to plot a histogram. You can read the code if you want to know exactly what these different things are doing, but basically we're just adding layers to a plot as if we were making a cartoon or something where you have the background you draw it first and then you put something else on top of it. And so we have this ggplot. And so what this shows is on the left-hand side are all the different simulated degrees of transitivity we had in our network. And on the right, in red, that's the degree of transitivity in our network. So right now, it looks like we have a lot more transitivity in our network than you would expect by chance based on random simulated networks with the same distribution as your network, right? But there are a lot of other factors that might influence whether, how people are making ties rather than just the degree distribution. So for example, people are way more likely to make ties in the same grade, right? So instead, we might want to simulate a network instead based on the degree of same ties in your grade. Basically, we're making a random mixing matrix. So we can do this by using, we can first create a vector called grades. This is just all the grades of the people in our data set. And then we're going to create a mixing matrix. It's just a 2x2 table. And it's showing all the degree of friendship ties in your data set that are of the same grade or different grades. So 52 of the ties in our graph are made between people who are both in 7th grade, etc. And so the idea here is, okay, we're going to try to simulate now a more realistic random graph because maybe this is inducing transitivity, right? When you have smaller networks, sometimes you get more transitive ties by chance. You're more likely to nominate a friend of your friend just because there aren't that many people to choose from. So we're going to try simulating a different network manually and comparing those networks' degree of transitivity versus our own network. So here again, we simulated a bunch of network. We just repeated all the other things we did. So instead here now we're using this mixing matrix function where we're creating networks based on the mixing rate matrix we supplied to the function. And so now again, we have all these different estimates of transitivity in these mixing matrix. And now we want to compare, okay, how do these simulated networks compare to ours? And the idea is that if they're similar to our network, then we can assume our network isn't special. Transitivity isn't unusual in this network, more unusual than you expect by chance. There's no preference for transitivity. But if it's different, that means that either our model is still bad or there's more transitivity than you expect by chance. And here you see the values of transitivity in this network are higher than they were in the last one, but they're still nowhere near our network. So people are selecting friends of friends when you account for the mixing matrix, the preference for people to nominate people in the same grade. But even when you do that, you still don't get a network where people are making friends of friends as often as you would expect by chance. And the point here is, well, now we can say, theoretically, this isn't the best model at all. We could say, oh, I guess people tend to select each other more than you expect by chance if they're a friend of a friend. There's a norm of me liking friends of my friend. And you can notice too, like we're repeating a lot of syntax here. Ideally, you put this in a function. R is a function-oriented programming language, so a lot of times you put lots of big things in functions, and instead of looping this in a for loop style, instead you're basically kind of looping within functions. If you want to look into it more, it's totally worth it. You do that a lot later on. Let's see, let me just make sure I'm not missing anything. Yeah, you can do all this. We're using SNI. You can do everything we just did in iGraph. And let's see. Yeah, so we just did two different simulations, right? We did a random mix. We simulated graphs based on a random mixing matrix, and we simulated graphs based on the distribution of ties in our network. We could theoretically do another mixing matrix where we accounted for both those, or maybe we also accounted for people's preference towards having friends of the same sex. The thing is, this gets more and more complicated, and it's really hard to do it with this, this manual simulating style. That's what we're going to use ERGMs for, but we're going to get back to that later. So all the things we just did, you can basically do with what's called a cug test, and it will basically simulate networks for you under the hood and compare some sort of factor that you care about in the network to your network. So for example, this one is simulating networks based on having a similar size as your network. And what it's doing is simulating all these networks under the hood, and it gives you this weird output. And the output saying it ran 1,000 simulations to generate networks just based on the same size as your network. And of those, your network happened to have a transitivity of 0.375. Of all the simulations, none of the simulations had a degree of transitivity higher than in your network. You could do this based on the edge distribution and also based on the dyad census, the degree distribution like we did earlier. So this is a CUG test. We do it all the time. I think you went over it before, but just to give you a sense of that's what's going on under hood and CUG tests. And so we're using these randomization techniques a lot. So now we're going to just quickly look at QAPs, which are called Quadratic Assignment procedures. So we talked about this in class a little bit, and the idea is, well, if you want to know two different networks, two different relationships within your network of people are related. Like, for example, you might want to know, is being in the same grade correlate with being friends with each other? You might want to know that, right? And classically, you might just run a Pearson's correlation coefficient on that. But that tends to give you very biased p-value estimates because it's not accounting for the fact that some people might be sending more ties than others. So we have these tools called QAP, Quadratic Assignment Procedure, for determining how correlated two different sort of networks are based on randomly permutating ties among friends, keeping the same overall network structure. So we're going to look at sex and grade. So we're going to create variables in our graph for sex and grade, and we're going to turn these into matrices. Basically, let's see. So you have these matrices so the first three values of sex, for example, is 1, 1, 2. I think that's, what was that, girl, girl, guy? And if you look at the matrix we just created, the distance matrix, it's 0, 0, 1, 0, 0, 1. And what it's saying is it's estimating the distance between these two people on this particular attribute. So 1 and 2, how far away are their values from each other? Well, they're both 1, so they get 0. 1 and 3, how distant is its value from 3? It's, well, 1 minus 2 absolute value is 1, right? And we do this down. And so we just create a whole distance matrix based on similarity across sex and similarity across grade. And so we could try running like a basic correlation test. We could just run standard old Pearson's correlation coefficient. Oh, did I not create everything? Adjacency matrix not found. I'm sorry. I'm just going to quickly run everything over again. Yeah. Just want to make sure we're at the right spot. In the meantime, do you guys have any questions? Anybody having any trouble implementing anything? You're all good? Okay. All right, so, I guess I didn't create the adjacency matrix. Oh, I make it right down here. Whoops. So I create the adjacency matrix right down here. So really we want to slide this down here. All right. So we create an adjacency matrix from the network we already had. So this is just, again, it's a matrix of whether or not you're tied. You get 1. If you're not tied, you have a 0. Most of the values here are zeros. And we could run a correlation between same sex and being friends. And we'll get this correlation of negative 404. This is actually a correlation of being different sex and being friends. So if I have a value of 1 on sex and friends have a value of 2, we have more different sex. So people are less likely to nominate friends who have different sex. But this is a correlation, it's a relatively small correlation, and we get these p-values from standard correlations. And this is really small correlation, but it's actually biased. These are almost always biased so that it estimates a higher p-value, a lower p-value than it really should, because it's not accounting for the fact that maybe some people, like maybe girls tend to nominate more people in this network. and you might induce a correlation just by the different out degrees of these different people. So instead, that's why we use QUAP. QUAP, the syntax looks a little wacky, but it's not too bad. So here what you're doing is you're listing the two different matrices that you're going to look at the correlation of. You tell it to look at the correlation and run it. And so it just simulated a bunch of different networks by randomly distributing the ties, and it's looking for how correlated are this grade matrix and this adjacency matrix compared to a bunch of matrices where you distribute the ties randomly. And so here we run a summary function, and it shows how many of these 1,000, I think it's 1,000 or 500, 1,000. By default, it simulates 1,000. It's saying how many of these 1,000 simulations we ran had a higher correlation, more positive correlation than in our model. Here, it doesn't simulate a single graph by chance that happened to have a lower correlation than ours. Every single one is higher. Remember, the correlation we have is very negative. The correlation we have for this is negative 2.8, negative 0.28. And so here, again, this is saying that if you're more distant in grades, you're less likely to be friends with each other. And it's saying compared to if you just distribute the ties at random, it seems like these are very highly correlated, even regardless of that. You could do it again with sex, which is the example we had. It comes up with the same correlation coefficient, because the correlation coefficient doesn't change, but the p-value changes a little bit. Here, I think we had 10 simulations where the correlation was lower than what we had, but that's only 1%. And we could interpret this exactly like a p-value. We can say, well, it's a less than 1%, about 1% chance that we'd see this correlation at random. We can probably assume that this is a real negative correlation. It's not 0. That's how QUAP works. And then there's MR-QUAP. It's what if you want to compare the correlation of multiple different networks at the same time. So here, what if we want to see how correlated is grade, having a similar grade with being friends, versus while controlling for how similar having the same gender is as friends. This can take a little bit longer to run. Basically, now it's permutating across 3 different things rather than 2, and so it squares it more than squares the computation time. So we run it and we wait 2 seconds. And let's see. All right, we're doing good. Okay, we got it. So we can now get a summary of the QUAP we got. And here what we're doing is we're getting these, this is like a regression model. And we're getting the correlation, the outputs kind of sucks, but this is our best QUAP tool. So here it's giving us an intercept, just saying like, just think of it as like a baseline correlation. X1 represents, so the dependent variable here is adjacency matrix. Are you friends or are you not? X1 here represents the grade matrix. So how correlated is grade matrix with being friends, controlling for how correlated being different sexes for being friends. And here you see, even when you include both of them at the same time, both being a different grade and a different gender are still both negatively correlated with being friends. And this is a classic tool that we often use for looking at different correlations and getting a sense of how big one correlation is versus another. But it's not the most sophisticated tool yet. We're going to look at one more before taking, I think, a quick break. So this is so say you have some sort of data and you have a lot of no-level attributes that you care about, and you happen to have networks for that data. And like, say you're looking at office space, right? And you're interested in, I don't know, how many hours they work, and you're looking at, their family situation, all these other things. And you're like, well, maybe sharing an office would also matter a lot, and I have all this information on shared office space, right? So maybe I should try to control for that rather than just pretend these people are independently existing in their own little spaces within this office. Basically, doing sociology. And so here we're first going to run just a standard regression model. Just does your grade and your sex predict your smoking behavior? So if you've used R before, the GLM function, this is just a linear regression. Here it's saying our Y is smokes, our dependent variable is smokes, as determined by grade and sex. And so if you do just a standard linear regression, you get here the estimates are tiny, the p-values are tiny. So it looks like your grade and your gender don't, at least within this tiny little network, predict whether you smoke. But here we're not at all controlling for whether or not you're friends or the smoking of your friends. So you could think of this as kind of like a almost like a peer influence model, except the idea here is it's a single wave, so it could just be correlated through other things. This is classic peer influence versus selection versus influence sort of problem with these models, but it can still be useful for getting a sense of for weighting by the network itself. So here we run a linear network correlation model. And here it's actually a very similar model specification. Here the syntax is a little different, but it's mostly the same. So here, again, welcome to R. Here, our outcome is still Y is smokes. Our predictors are grade and sex. And here we have this weight 1, and it's equal to our graph. And basically, it's weighting for the degree of smoking among your friends. And so if we look at what our model gives us, let's make this a little wider so we can actually read this. Let's actually rerun it. Neat little trick, if things are not fitting every so well, and you extend it and you see it's still like there's a lot of blank space. If you just run it after you extend it again, it'll now stretch out. So here we have our model. Still, grade doesn't matter much, and smoking doesn't matter much for grade, and sex doesn't matter much for smoking. But this row, that's indicating the degree of smoking among your friends, and there it's super significant. So here we could at least say that people's smoking behavior tends to be associated with their friends' smoking behavior. You could do this a lot, actually. The models I often see this for are whether they want to say the network isn't confounding things. That's one of the more common uses I've seen for the linear network correlation model, or LNAM, I guess. We're going to take I think a brief, like 5-minute bathroom break, and then we're going to get into ERGM. We're doing good? Okay, great, thanks. Well, interrupt the conversations, but day is young. All right. Sorry about that. All right. Did any of you have any questions you want to ask me before I go forward? Okay. You can save them to the end if you don't have any. Or maybe, I don't know. We'll find out. I'm not sure nobody asking questions is ever a good sign. But maybe in this particular circumstance it is. Who knows? All right, so we're going to work on exponential random graphs. Now, if you remember, before we were talking about how we were trying to determine like transitivity, whether transitivity is a really big norm in a network or not, right? And what we were talking about before is that to measure whether or not a statistic like transitivity is big in your network, the way you would normally do is you compare it to random graphs that you're drawing. You would compare it to random graphs that have similar distributions and a lot of different factors, right? And it's saying that you could try to factor different things like grade matrices in. You could look at the degree distribution. You could look at sex, whatever. But the thing is, when you have all these different things, it gets way too complicated to simulate on your own. So that's why we have exponential random graphs. These exist so that we can try to determine what factors are determining friendship selection in a network that we have. And we can look at multiple different factors that might be affecting friendship selection simultaneously. The way the random graph works, just to give you a reminder, it will give you output that looks that's in log odds. It's basically it's simulating the whole graph and is actually really trying to estimate a graph that fits the input you're giving it. But you can interpret the log odds as the output as people are more or less likely to be friends if they have these same sort of characteristics. In essence, you could think of it kind of like a logit model, But the reason we're not using logits to do the same sort of thing is because, well, there's two big issues. First, a lot of the parameters that you're interested in, like transitivity, those are heavily related to your y. And when you have, basically when you have your y on both the left and right side of the equation, ends up with a lot of biases. And the other problem is that when you're just doing a standard logit model, there's no way to account for the fact that some of the parameters you're looking at are interdependent. So if you're, say, you're looking at transitivity and force cycles, or a friend of a friend of a friend is more likely to get nominated, these things are interdependent. And in a logit framework, it's not necessarily going to capture that, but in an ERGM framework, it will. It'll account for that. So ERGM is one of our best tools for determining what sort of factors influence friendship selection. And the logic behind ERGMs is very similar to the logic behind the Siena models that you're going to learn tomorrow. So if you want to understand selection versus influence, you have to figure out selection first. And so this is the selection side of the equation. Let me see, just want to make sure I'm not forgetting anything. Okay. Yep, okay. So, all right, so we're going to do some house cleaning. We're going to delete almost everything in our environment because we have all these variables, and a lot of times when we're looking at our environment, we want to look down for different variables to get a summary of it, and it's just too much. So we're just going to keep our network object, G, and our parameters for in degree and out degree. And so here we're identifying the variables we want to keep, and we're creating a list of all the objects that are in our environment. So ls that provides a list of all the objects in your global environment, and here are all the names of the variables that we have loaded already. And here we're assigning it to a Tibble object, which is just a data frame. Again, we're just converting it to make it easier to use for, well, to make it usable for other functions that we're going to use. And we're going to, so we have this object that states all the variables in our environment. And here we're just going to filter out the variables that are the ones that we want to keep. And so we're going to say, just keep all objects where not in our list of 3, where it's not G in degree or out degree. So we create this, we update this variable. So now it's listing all the objects in our environment other than the 3 we want to keep. And now we're saying here, get rid of all the objects we have, plus the object that we created called all objects, and just keep the ones that we care about. And so we do that, and now we just have the graph and these 2 other parameters, the in degree of each person and the out degree of each person. All right, so the dumbest ERGM that you could run is basically it's a Bernoulli distribution. It's simply estimating a graph based on the degree distribution of your edges. And so that sort of graph takes no time to run at all. And so here we're getting summary statistics. Let me pull it up. Oh, good. Okay. No, it didn't. Never mind. Here we go. Okay, so here we have this formula. We're estimating the graph. We're saying simulate a graph based on the input we give you. And here we're saying based on the degree distribution. And here all it's saying is, okay, you get this estimate of -2.7. And it's saying basically the log odds of someone making a tie with anybody at random is really, really small because most edges in your graph are not filled, right? Most edges are zeros. There are some people who are being selected, but overall, not a lot. It's not usually like interesting, but it is a useful, you could think of it like a constant. If you, and it's always going to be negative if you have a very sparse network. So this estimate for -2.7, one of the things you could do, so we could assign that to an object. Let's assign that to an object called coefficient. So this is the coefficient that we got from the graph. Grab just the estimate, the -2.7. And if we wanted, we could convert this into probability using it by exponentiating it. And when we exponentiate, like, this is a standard exponentiate sort of thing you get on your graphing calculator or something. And we're just saying exponentiate our log odds into probability. and we get probability, it's 0.061. That's the same number as the graph density. These are related. The graph is trying to, the random graph model is trying to estimate here a graph based on the degree distribution of your network. So when you exponentiate its coefficients, what you should get is something that is the equivalent of the density of the graph. So ergms, though, obviously, you never run an ergm like that. Usually they have like, I usually see them like having like 10 to 15 variables in them. There's a ton of different sort of terms that you could use in your ergm. You can pull them up using this question mark. Question mark is always how you pull up any documentation on any function you want. Here, if you pull it up, I usually prefer to go to a website when I do this because what you get is this long list of all these different sort of terms that you could put in your model. And it's a little overwhelming and really hard to read here. But the idea is, so instead of just estimating a graph based on the degree distribution, we might want to estimate a graph based on homophily. So for example, we could say, we could assume people tend to have preference for having friends of the same gender when they're in high school, preference for same grade, and preference for having the same sort of smoking habits, right? And we could say, okay, simulate a bunch of models based on these outputs and try to come up with coefficients for these outputs that would create a graph that looks as similar to our graph as possible. And it's doing this through this MC-MC iterative process. So it's coming up with an estimate for some sort of beta for preferences for having sex, and it's updating it to get a graph that looks more like the graph we have. So we run this. This one is simple because we're not actually including many any sort of interdependent attributes. We're not using a lot of the different graph features we have. So here we'll get an output of preference for different sort of ties. And so here we'll see, again, you can think of edges like a constant. No match is, do people tend to have a preference for having friends of the same sex? It says, yes, you do. Your log odds of befriending someone is 0.46 if you're the same gender. Increased by 0.46 if you have the same gender. If you're in the same grade, your log odds of, it's a mess to talk about log odds, which is why we exponentiate these, but the idea here is that it's saying that you're much more likely to nominate someone as a friend if they're in the same grade. You're a little bit more likely to nominate someone as a friend if they're the same gender, and you're a little bit more likely to nominate someone as a friend if they're also smoking as the same degree of smoking as you. And this is controlling for the effect of all these other things on your nomination. And here we'll get statistical significant scores based on the trials we're getting, like how likely is it that these factors are influencing your friendship selection. And so we're getting significant, but this is still a pretty this is still a pretty naive graph. And one of the ways we could actually estimate is this like a good model for our network is by using goodness of fit functions, based GOF, that stands for goodness of fit. So ergm comes with a lot of goodness of fit functions. You're going to be using them a lot when you work with ergms in your own work, because you want to make sure that the graph that you're modeling actually like resembles, that your parameters in your model are actually creating a graph that looks like reality. Because if they're not, then chances are your model isn't well specified. You don't know if these are really the factors determining your network, and chances are they probably aren't. So here we create this, we run a goodness of fit algorithm. These can take a long time, and now we're going to plot the results. One of my gripes with the ergm function is that it plots all the goodness of fit statistics at the same time, and it shows you the last one it's doing. Let's start with the earlier ones because these matter a little bit more. Well, the last one probably matters the most, but in a sense, we'll get to that. So here we're looking at of the simulated graphs that we have. We're getting these box and whiskers, these distributions of, in the different simulated graphs we have, what's the proportion of in-degree, what's the in-degree distribution? So how many people have 0 incoming ties? How many people have 1 incoming tie? How many people have 2 incoming ties? And then this line is what's actually in our network. How does the degree distribution of the simulations compare to our actual network? And if our line fits within these box and whiskers, that usually is okay sign. We actually usually we'll usually evaluate the whole degree distribution with a few different statistics. But here, I guess the in-degree distribution looks, I mean, it doesn't look that similar, but on the grand scheme of things, it's not terrible. But same with the out-degree distribution, except if you look at the out-degree distribution, this happens a lot. So here it's saying a lot of people in the real data are nominating no friends, but in our simulated data, very few people are nominating no friends, suggesting that we might need to add a parameter to make our model more realistic of the graph and represent the fact that there are many people who are not nominating friends. Edgewise shared partner, this is a measurement of transitivity, and the idea here is here it's saying that in our simulations, there tends to be a lot less transitive ties than there is in our real graph. And one of the reasons why is we're not even actually modeling for transitivity yet. So this would be, once I got to this, I'd probably say, okay, this is no good. I need to add transitivity into my model. There are more and more of these. Geodesic distance is important too. That's kind of like 4th most important in my list. And here's just like standard goodness of fit statistics for like the actual estimates you have. This almost always fits in my experience, but maybe I'm wrong. Maybe my experience is not so great. Who knows? Or maybe it's very good given that it always fits. But all right, so we could try to run a better model since this didn't fit the data perfectly. The simulations that we're doing didn't come up with a graph that really looked like reality. And because of that, we can't really trust our estimates for what's causing people to select friends. So we might try a crazy model where we have individual coefficients for every sender and receiver. So we have some sort of parameter saying like this person's unique, they're a little special, whatever, and you know, we're going to give them their own little estimate. And so this will give you some fit statistics, and the Bayesian information criteria is, you know, that's a standard fit statistic what we would use to measure, you know, how good is the model fitting the data versus how parsimonious it is, how simple is the model. Is it, if you have more parameters than you need in the model, generally suggests that the fit isn't so good. Here we have like 1 billion parameters in the model, and they don't really mean a lot to us. So this would suggest that this isn't a great model either, because it's not very intuitive. We don't know what to make of all these sender and receiver traits. Are these people really that special that we can't come up with a better model to generate the graph? And so again, we could run you know, the goodness of fit statistics, and they should be extremely good because we've really overspecified the model. Just look through these really fast. Well, it's better than the last one. A little, it's not the best, but it's okay. Okay, so we could try then. One of the things with ERGM models is it is recommended that you try to like build them very slowly, because as you add parameters, things can go kind of bust, which is kind of why I'm adding 1 parameter at a time. So here we could add statistics for in-degree and out-degree. We could control for a fact that some people are just naturally more outgoing or naturally more likable or popular in this model to determine our network. We can run that, and this sec. So this also should make a lot of intuitive sense. You know, people who have higher in-degrees, this parameter for in-degree is helping our, is meaningful for our graph. People with more out-degrees tend to select people, I believe, more people in general. It seems people with higher in-degrees tend to select more people in general. We could look up the individual term if we don't understand like what no I covariate means, and it gives us this jumbled text that does have meaning, but I'm not going to read it through. All right, so then we could start adding more higher level network features. Like we could add transitivity terminal, which is what we were talking about before. Well, first we're going to add reciprocity terminal, right? So reciprocity, again, it's a propensity for people you nominate to nominate you. It's very common among most species. If you say you like the other person, they're more likely to say they like you. And so we can include that in our model. And now we're getting the MC output. Basically now, because we have a term that actually has to do with interdependencies among the nodes, it's doing more of a simulation style to get our graph and updating. And here what we see is if you have a reciprocal, if you nominate someone or someone nominated you, you're way more likely to nominate them. So we could consider putting transitivity in our model. And I don't recommend running this on your computer because this is going to break. But there's a reason it breaks, and it's important. So so triangle is just the propensity for you to nominate a friend of a friend. And the problem, this is like one of the most common things you find out early on with your use of ERGMs. It almost never works. And the reason why is so in large networks, most triangles go unfilled. And so what the model will start doing is it'll start oscillating between saying everybody's tied or nobody's tied, because this attribute, I'm going to stop this from, oh, good, it stopped itself, thank God. The model will basically, it'll not converge because it'll try to, it knows that the triangle parameter matters, but it won't be sure how much it matters, and it'll think, okay, maybe it matters a lot, but then, this network we just simulated, everybody's tied with each other. And I'll say, okay, maybe it doesn't matter at all. But then it's like, now nobody's friends with each other. And so it goes back and forth, it never converges, and it'll give you an error. So usually when we run ERGMs and Sienna models and all this, we use different variations of transitivity measurements. There's a cheap trick you could to get around this, where you tell the ERGM to only run a few iterations so that you could get something for transitivity. But you never do this to publish a paper. This is just if you really, really want transitivity in your model, and you at least want to see it. I'm not even going to bother running it. Although I do have my MC diagnostics here, so I guess I'm going to run it. But here we're going to see that the model doesn't converge very well. Well, first of all, so it's only going to run for a couple iterations. Should be quick. Almost there. Okay, so it's run its 2 iterations. Now it's, again, the log likelihoods. Okay, so we have this model. We see, oh gosh, the triangles, they seem to really matter a lot. People are definitely nominating friends of friends more often than you expect by chance. But if you run some diagnostics on like how well does this model fit the data, I believe Jim showed you some of these earlier. Why is this not running? Come on. One sec. I'm just going to reset the plot space because this should give you. Okay, good. Here we go. Okay, so here it's showing what are these parameter values in the, as your model is updating over and over and over again. How many mutual ties is it estimating? I'm sorry, what's the value of mutualism? What's the value of triangle? And the idea with MCMC is you want to converge. You want to hit a stable point where it can't update, can't get better than it already was. But here, it's changing so much. That would suggest that it hasn't converged yet at all. So this is a terrible model, and we shouldn't use it at all. If we want, we could also we could pull out an example graph from the simulations. I think this is actually one of the cooler things. What are you giving me? Warning message. Huh. It should work. Margins are. Yeah. Well, let's see. Here we go. All right. So here is an example of a network that's the model simulated. This is, and it looks like, I don't know, did it look that similar to our network? Maybe. I think there's a lot more transitive ties than before. Our model before was more modular, more clustered. It wasn't just a big circle, but rather different branches for the different grades. So given that just by eyeballing it, it doesn't look that much like our network, there's another way of saying, okay, this model isn't working. But looking at these can sometimes help you figure out what statistics we need in our model. So a really good alternative to like the triangle term is what's called GWESP, or geometrically weighted edgewise shared partners. It's basically a measurement of how close you are in the distance space, and it says that if someone's closer to you in this network overall, you're more likely to be tied with them. But people who are far away are less likely to be tied with, even if you have one friend. And the idea here is that it doesn't try to assume that you're going to become friends with someone who's only friend with one friend of yours and nobody else near in the network. So GWESP is a common term we'll often use to measure transitivity. In papers, nobody minds it at all. They're like, oh yeah, I get that. It's really standard. These things take a longer and longer time. Oh, okay, this was finished actually only after 4 steps. This is good. So with ERGMs, by the way, I think its default is to run like 20 iterations before giving up. Basically, these are models. MCMC algorithms could technically, go for infinite time if they're not converging well. So you can alter that if you think, oh, maybe it'll converge, maybe it'll get there. But we're not going to go through that right now. We're going to do some basic. All right, let's pull this up. So here are the results from our new ERGM. And here, instead of the transitive ties, we have this GWESP term that's basically like transitivity. And it's saying that people tend to be more likely to nominate others who are friends of friends who are relatively close to this network. It has this term. This is kind of like a GWESP decay. You could think of it almost like maybe like a squared term. Yeah. Actually, I don't think Sienna prints the GWESP display, the GWESP decay or not. But basically, so now we have a model. We have now mutual ties in our model. We have reciprocal ties. We're accounting for people who tend to be more outgoing or less outgoing, people preferences towards having friends who smoke, being the same grade. And we can run some diagnostics on it again. And spoiler, still not great. Well, actually, this doesn't look so bad. So it converged. Let's see. Simulate. Oh yeah, here we're just pulling out another graph from this. It looks a little bit more like our network. Still not as clustered as I'd like as our network. But yeah, I think that's the gist of ERGMs. They get complicated, they get large, they can take super long the bigger the data you have. If you have like 2,000 nodes, this is going to take a really long time. Yeah, so I think that's it for ERGMs. We're going to quickly go through diffusion, but do you have any questions on implementing ERGMs before I go on ahead? Yeah?
So if you said that that's not exactly what you're looking for, what might you be looking for?
Right. So I want a network that looks just like, one sec. So by the way, let me just, so this source function, by the way, this is a way of just saying run that script. So it's a cheap way for me to run the script. So I want my network, actually, this one's harder to see. I want the network to look a lot like this. Notice how there's a lot fewer, like, it seems broader. There's not like a really popular common core. These people are kind of popular, but like in the other model, it was like there's a really popular center and everybody seems kind of friends with each other. But in reality, here it seems like no, there's really strong cliques from each other. So I want my algorithm to end up looking something like this. The plot, looking at the actual simulated plots, that's kind of like an eyeball test. It's usually in a paper you won't include that as a goodness of fit test. It's more helpful for you to get a sense of what do I need to change in my graph. Because in theory anyway, these ERGMs are all supposed to be guided by theory. You're always supposed to have a sense of, what factors are influencing my graph to form. In in reality, a lot of times people, they have a theory and it doesn't work so great, and they add parameters and delete parameters, and then they play with these. Sometimes they'll get a graph that looks really good, but then they'll add a couple more parameters, and old parameters before didn't look so good, and they're not sure which one's better, so then they'll start doing goodness of fit tests. And it's a lot of doing this, but it's really fun and really cool actually as you do it and you get comfortable with it. Any other questions? Okay. Jim, do you have any comments?
I was just going to say that, for a network like this, I would probably put a constraint on the out degree to match the design. So in this case, there's it's a limited, you couldn't nominate more than 10 nodes, and 5 male and 5 female. So you can put a constraint. There's a whole series of estimation models where you constrain the sample space for things like that. So my guess is if you were to constrain the out degree to not be greater than 10, if you were to match on, I'm going to say the number of isolates in the network or something like this, assuming those were, or the number of people nominated 0, those are some of the things you might do. Theoretically, in a case like a school, I'd probably include a differential homophily by grade. So instead of just grade match, I would say that I'm going to allow the 7th graders, both 7th grades is different than both 9th grade, that kind of thing. So those are the kind of features you go to flesh out these models a little more.
Yep. Yeah. You basically always include if there's a limit on how many people your participants can nominate, you definitely always include that. Because then when you're doing the goodness of fit test too, you'll end up with people who are having out degrees that don't exist in your data. And that's usually a big red flag. Yeah, so there's a lot of, those are good examples of things we can.
I mean, the logic of all of these randomization kind of tests are that, unlike when your null hypothesis is 0 and you're happy when you get something that doesn't match 0, what you're trying to actually do here is build a model of the network that your observed network is a reasonable draw from. So the logic is you're trying to build a random class of graphs that the graph that you've observed in your actual sample could plausibly have been a reasonable sample from that class of random graphs. So it really is a fitting process as opposed to a rejection process. And then the idea is that if you've done that, then you probably captured the most salient features of the observed social space.
I think you mentioned earlier too, you can pull these simulations out too. So if you wanted to do simulations on other graphs, once you estimate a model for data you know, you can then create more realistic versions, alternate universe versions of data you don't have. In fact, a lot of the diffusion models that we look at, they're built on ergoms. I know the epi models are. I don't know about the net diffuser. But yeah, they're based on these sort of processes, the ergom algorithms. So, okay, so we're going to now do diffusion models really quick. I'm not like an expert at all on this. If you want more detailed info, there's this really good tutorial online from StatNet, and I ripped some of this from there. Here I'm just trying to give you a really high-level sense of like, okay, how do you simulate a model? How do you simulate a disease diffusing processing? Maybe the CDC contacts you and they say, oh my gosh, 4 people are infected with this new thing. How long do we have before society breaks down? Well, now you'll be able to tell. No, not really, but it is basically the sort of models. So we're going to use the package epi model first, and this is for doing what are called SI models and SIS models and SIR models. And so basically this is, are you susceptible to getting disease? Are you infected with disease? And there's variations of these where maybe the disease, maybe once you get the disease and you survive it, then you can never get it again. Or maybe but then there's the SIS where, oh, you can get it again, basically a cold or something. So these are the type of models that we're looking at right now. So here, first you want to create a network of some sort. First you're just prepping like an empty matrix essentially, but it's a particular network object. And you're saying, okay, I want there to be 500 nodes in it, or vertices as they're called in the SMA framework. And this is made by the SMA people, so you notice a lot of the output looks very familiar. And so here we're going to formulate how people are getting linked in this network. We're going to we're creating our own version of a random graph based on our own sort of algorithm, and this has ergms under the hood, and I don't know why that thing keeps coming out. Well, anyway, so don't worry about the warning messages here. This is just, sometimes R1 has a bug. It'll repeat a warning message that I meant to tell you like 3,000 lines ago, and that seems to be what's going on. So you can, all right, so you create a sort of a function for creating this network, and it's based on the dyad distribution and also concurrency. And let's see, so so now we're going to come up with some target statistics for what we want the network to look like. How many edges do we want to have? How many concurrent ties? So again, concurrent tie, that means like someone that you're having sex with is also having sex with someone else in this framework. And so here we're going to specify how many simulations we're going to run. So here it's a model. It's based on like a series of steps. Something's going to happen every step in terms of how the model's diffusing, how the disease is diffusing, and it's going to be happening randomly. We have to set a certain duration for it. Third, we're going to set it to 50 steps. This is pretty common underlying function going on underneath a lot of these sort of models. Let's see. And so now we're going to create a model based on these estimates. So we're estimating this is called ergm. It's like an ergm, but it's longitudinal. Time is the T what it stands for. So we've created now a network that we're going to have this disease diffuse through. And let's see, we're going to get some basic diagnostics for it. And take a few minutes. I think this takes, not a few minutes, I think it takes like 30 seconds. So you really want to always start small with these before you get bigger, even if theoretically you're really interested in the big processes, because they do take a long time. There are things we could have done to simplify this, but this is a pretty simple model. All right, so we created some diagnostics. So this is showing our simulated model versus what we wanted the model to be. So we told this ergm that we wanted there to be 175 edges. Well, in the simulations it created about 179. That's pretty close to what we wanted. We said we want 110 concurrent ties and produced 112. That's pretty close. So the idea is you want to create, you have these goals for what your model looks like. You want to make sure that what your network looks like. You want to make sure that when you tell them to create these random networks, that actually looks like what you were hoping for. Sometimes you can misspecify the model so that the statistics, the target statistics you're looking for are impossible. And this is kind of why we do this first. Let's see, so we can look at it over time. Right. Oh, yeah. So this is showing in these simulations, over time, like if these were to keep running, are the edges changing? Are the mean degree changing? Are concurrency changing? The hope is that they're relatively steady, because when we run our disease through this, we're hoping that the network isn't changing too much. What we're really interested in is how's the disease spreading through this network that has these features that we assume are relatively stable, I guess. And so now we're going to, so we create a network for our data. Now we want to create a disease to spread through our network. We want to kill these people off. And so we're going to set some parameters. So we're going to indicate, again, so this is 50 time steps are happening, and each time step we want different things to happen. So here we want there to be a small probability of someone getting an infection that their friend happens to have. We want people, this probability to happen multiple times, 2 times per partner, and we're saying how quickly will people recover from this disease. We're going to indicate how many people are initially infected. This is really standard in these style models. It's just a a number that we're deciding here. So we're saying, okay, 10 people in this network are infected, and they're going to be infected in random positions. You can, I believe, indicate exactly where they get infected, but here in our model, we're just indicating that 10 people in this graph are randomly infected with this disease. And we can specify the type of disease. So here, people can get sick, they can recover from it, and they can get sick again. So we can think of this as a cold, and we're interested in over time, how will this disease spread through the network? And so here now we take our disease diffusion parameters and the networks we estimated, and we're going to simulate it. Disease going through it, and I might. Oh, I'm just going to run these because I skipped a thing. Sim. All right, so now it's going to simulate the network. So here it's running 500 iterations. You can disable this from showing if you want. I kind of like it, so I know that something's working rather than sitting and waiting and hoping. So here we're running 5 different simulations of this disease diffusing through networks, and we're diffusing for 500 different time steps, and it's indicating the prevalence of the disease throughout these networks over time, and the rate of recovery and the rate of new incidences. And it's almost done. As I said before, these take a while, and this is not even a big one at all in the grand scheme of things. So we're almost done. Okay, so now we're going to plot the number of people who were infected versus the number of people who are susceptible. So you often see these here where it'll, in these type of models, you'll hit an equilibrium of a certain number of people tend to be infected at a certain rate, and a certain number of people tend to be healthy over a certain rate. It's a common outcome of these, and that's kind of the point of this model, is to show like, oh, the disease is always going to be in the town based on these parameters, and a lot of people are always going to be sick, and life is terrible. So the cool thing too is you can actually look at, so again, dev-off, by the way, is your best friend if you're not used to it. Dev-off tells R, completely forget all the settings you put for your plot space before, we're going to just reset it. And so here we got our network, and you can see ties between individuals. We can see the red dots are the people who originally were sick, and we could look at over time at 500 in the same network, at time 500 after the disease has gone around for a while. What does a network look like? And I love these graphs. So here you can see, oh my gosh, red's all over the place, and look how they're connected, and nobody's safe. But you know, it's a neat little, it's a useful output. So that's like the smallest tutorial and the least like coverage of this package I could possibly give and get away with. There's a lot more to look at. I highly recommend if you're interested in these type of models, going on their website. They have a ton of information on it. We're going to jump to like the other most common diffusion package for simulating diffusions across networks. This is made by Tom Valente, who Jim keeps mentioning, because he's really great in this world. And so it's a different framework for simulating networks. These are really good for doing threshold models and complex contagion models. So for example, if when you're looking at like diffusion of some sort of innovation, right? Maybe everybody's getting Facebook. Facebook is new. You know, some people like I'm not going to use Facebook when I first come up with that. Nobody's on it. I don't care. But there are some people who might, right? You can imagine maybe different people have different thresholds for how many people need to be on it before I use it, or maybe they need to have some sort of set for how many of my friends, what proportion of my friends need to use it before I use it. And so these models are really good at looking at those sort of attributes. Since the diseases, we could think like rumor spreading. That's the example we're going to use, or you know, an innovation getting diffused, getting popular. So you're going to find, even though the syntax is different, the underlying logic is very similar to the last, the epi models that we're doing, the epidemic models. So here we're creating we're simulating the whole diffusion model in a couple steps. First, we're saying how many nodes we want in the model, even 500, just like our last one. How many periods here? We're saying there's just a few periods of diffusion. Basically, how many times is this model going to be running? We're going to indicate the baseline graph. So here we're just going to pretend it's a relatively simple network that follows unrealistically nice features. We could actually input our own data into here if we want. We could say, I have this network I'm interested in, how rumors would spread through this network. Like here we're just going to create a network. We're going to indicate the chance that people are going to change friends. Number of people who originally adopted the thing when we started simulations, here just 5% of the network. The threshold for spreading, so people have to be friends, basically. We're not including any real threshold. We don't care if everybody, how many people in the network do it overall. And let's see, right, and we're measuring exposure as a count. So if more of our friends do something, we're more likely to, or more of our friends are spreading this rumor, we're more likely to spread the rumor, rather than a higher proportion of our friends or whatnot, right? That makes a little bit more sense, I think, in this particular realm. So then we could run this model, and we can create some summary stats for it. And 1 sec. All right. So we get some summary stats. So it's showing over the course of time. You know, there's 5 periods here based on our model. How many people have adopted and have spread this rumor over time? So you know, we start out with 5 people. T1, 25 people were spreading this rumor. By the end of our 5 simulations, 125 people were spreading the rumor. We can look at, I'm sorry, this is how many new adopters there are. So the cumulative adoption rate is how many people overall on the network did it. So by the end of the network, we had 70% of the sample spread that rumor, or talked about that rumor here. So this rumor spread really fast. And right, so then we could also visualize these, because again, this is very similar logic to what we were doing before. And oh yeah, I like this. So here you can show how many people have spread this rumor at different periods of time. It's taking a while to load. I'm hoping it does. Okay. All right. So and also has the network changed over time. And I don't know if I'm going to get lucky. I don't know what's not doing. All right. So here we have period 1. There's just these 10 people who spread the rumor. Period 3, a bunch of more people spread it. It's adding a color for new people who adopted that's blue. You don't necessarily have to do that. And by the end, like tons of new people are adopting or spreading this rumor. And you can look at the rate of spread over time. And this usually follows a S curve. Doesn't look like it's really down here. Basically, at the beginning, it takes a while for the rumor to spread. And as it picks up, it spreads really fast. And then as it hits saturation of population, it stops spreading as much. So it usually kind of follows an S. If we let this run 10 more iterations, you would get a slower and slower kind of logarithmic curve. So yeah, so that's what I have for diffusion. There are a bunch of other methods. A lot of people who study diffusion create their own algorithms for doing it. There are a lot of packages that allow for it. These are 2 of the biggest ones, but even like Sienna, which are Linux models, they do have diffusion-like algorithms. And I think that's it. Thanks, guys.